Hello, Professor 42 here, again bringing you the next C++ debugging lecture. Today I want to show you another feature of the debugger that sometimes can be extremely helpful in debugging programs. But I'm also going to spend quite a bit of time today setting up a double linked list class for us. We're going to use it in several subsequent debugging sessions that deal with tricky debugging of pointers. Let's get started. A double linked list is one of the common container classes, and as you can see, there'll be a head pointer that will point to each of the successive nodes of the items we're storing in the list. Think of a double linked list as a grocery shopping list, for example, or a collection of friends' phone numbers, or what have you. The key items will be there has to be a pointer to the start of the list. There also must be a pointer that points to the rear of the list. Each of the nodes contains a pair of pointers that will point forward to the next node or back to the previous node. By having both pointers, you can go through the list sequentially from the front to the back, or in reverse order from the back to the front. That makes it a double linked list. Each node in the list has to contain the client data that's being stored. Exactly how we store the client data is what's important. What we would like in a container class is to be able to write it once and be able to store absolutely anything that you need in the list. That means we can't be specific about the client data. In our generic class, we can't, for instance, store phone number structures, because that means the list would only be good for storing phone numbers. And if you wanted to store baseball scores, it wouldn't work. We'd have to redesign it and recompile it and rebuild it. So to create a generic double linked list, we have to resort to using what are called void pointers. That is, it's a pointer, points to the client's data, but it doesn't have a data type associated with it, otherwise known as a void pointer. The other alternative to making a generic container class is to use templates, which are even more complicated than the simple void pointers. Of course, whenever we access a void pointer, we'll need to typecast it back to the type of data that the data pointer is actually pointing to. So what would our reusable double linked list container class look like? Well, we're going to first need to store the nodes. In this case, I've called it a link node, and it is a structure. And the link node is extremely economical. It takes up just 12 bytes, 3 4-byte pointers. First, we'll have a forward pointer that points forward to the next node or link node in the chain. That'll be followed by a back pointer that points to the previous node in the chain. Now, if there isn't another node in the forward direction, that forward pointer would be 0. If this is the very first node in the list, there isn't one previous to this, so the back pointer would be 0. And each node then has a data pointer that will point to the client's data that we're storing at this spot in the list. Now, our generic double linked list class will have to have, in this case, 4 data members. It's critical that we have a head pointer that points to the first item in the list and a tail pointer that points to the very last one. That way we can go both forwards and backwards through the list. In addition, we need to be able to keep track of where we're at as we're moving through the list. And so we'll have a current pointer that points to the current one we're working on, so that we can sequentially go forward or backwards item by item in the list. It is sometimes helpful to have a count of how many actual nodes or individual client data are being stored in the list, and so for convenience, so we don't have to keep iterating through the list and tallying them up, I'm going to store a count of how many items are actually in our list at any given point in time. What kind of functions would we have in the in the double linked list class? Well, certainly we would have an empty list so we can get rid of everything when we're done. But conceivably, the client might like to add a new item at the head of the list, or he might like to add a new item at the end of the list, add at the tail. Then, of course, there's always the insert option where he would like to insert this new one somewhere in the list. And to avoid confusions from the user, when you say insert here, does he mean insert before this spot or insert after this spot? I created two functions, insert after the current node and insert before the current node. That way the client, the user of the program, won't get confused as to where the actual insertion is going on. In addition, we'll need to provide a delete the current node so he can remove one item from the list when he's done using it. We'll also provide a couple of helper functions. Get size will return the count of how many items are currently in the list. We'll have a bool function that can return true or false. Are we at the head? Are we at the tail of the list? Those kind of simple functions. Now, when you're dealing with a generic double linked list or a generic container of any kind, we have a unique problem. And that is that the client might like to try to find matching data. Presumably the client has stored a bunch of data in the list and now he wants to look up a specific one. How can he do this? Well, we can certainly create a find node function in our double linked list class, and the client can say, I want to find student 1234, and call find node passing the data he's trying to match, the 1234. And of course, our code is very simple. We can reset the current pointer to the head, and as long as it isn't 0, we can check and see if this is the one he's trying to match. If it isn't, go ahead and move down to the next one in the list, and as long as we've got one, see if this is it. And then if we find it, we can return true, we found it, or false, we didn't find it. The catch with void pointers is that we don't know what data we're storing. All we know is it's a void pointer, or as I like to call them, idiot pointers. And what has to occur is we need help from the user. He knows what's being stored in the list, not us. So we have what is called a callback function. When we get a specific node in the list that we want to check to see if this is a match, we have to call back into the client program to one of his functions and give him the current data at the node we're at and the matching data he's looking for, and ask it, hey, is this it or isn't it? And he will let us know whether it is the one he's looking for or not. This is called a callback function. Callback functions are extremely common in programming. It happens all the time, particularly if you get into Windows programming. For instance, in Windows programming, very commonly, programs that do any type of text processing need to know what user fonts are on the system. And there's an enumerate font family that will you can call, and Windows will go through all the installed fonts on the computer, giving you the names of each one that's installed. But he will be calling back into your client program, your program, saying, here's one, do whatever you want with it, and let me know, and I'll go give you the next one. So these callback functions are a very common thing to have, but they are a little bit complicated when you first try to code them, mainly from the prototype. The prototype that we have, in this case, I'm going to call it, say, match on ID, supposing you're trying to match on a student ID number. In this case, we would be passed the pointer to the matching data that he's trying to look up. Again, we don't know what he's trying to look up. It could be a student ID long, in which case he'll give us a pointer to it, or it could be the student's name and he'll give us a pointer to that character string. In any case, I'll call it pointer to matching data. Now, we are pointing to a specific node in the list, and we've got the client data. We need to give him a pointer to that client data so he can check and see if this is the one he's looking for. I'm going to call it pointer this. So we will recall back to the client, giving him the matching data he's looking for and a pointer to the current data we're on, and ask him, are these two the match? He can return an integer. Well, you could say it's a bool, but realistically, he might want to do some sorting. So we need to know it'll return 0 if this is the match, but it'll return a +1 if it goes before, -1 if it goes after, so he can deal with sorting issues if he wishes to. So if that's what the function looks like in the client program, namely he's passed two constant void pointers, one to the data that we're trying to match on and the current node that we're asking him about to see if it is a match, how do we set up the client, how do we set up the prototype for this thing? This is where it gets tricky in our coding. The actual way to set it up is this way here. Obviously, the function is going to be passed two constant void pointers, a pointer to his matching data that he's looking for, and a pointer to the current data in this node that we're on, and we're asking him, does the pointer this, whatever this is this thing matching the data you're looking for? It will return an int. But it is critically important that we have a pointer here out in front of the name of our function, in this case findFunc, with a parenthesis around it. This reads, findFunc is a pointer to a function that is passed two constant void pointers, and that function will return an int. That is the prototype. The parentheses around it are critical. This set of parentheses are critical. If you wrote it this way, this says oops is a function that is passed two constant void pointers and returns an int pointer. Oops. So rather than trying to code this gargantuan mess all over the place in our client, in our double linked list class, I'm going to create a type define and create a new identifier, and I'm going to call it uppercase findFunc. And I'm type defing findFunc to being a pointer to a function that is passed two constant void pointers and returns an int. That means in my coding, when I create my prototype for the findNode function, or whatever we want to call it, it will be passed a pointer. The client will call me passing a pointer to the data he's looking for and the name of his function that we are going to call back into. So this find over here will be whatever name the client's program's callback function is to be named. What will its prototype be? Well, its prototype will have to be passed two constant void pointers and return an int. As long as it matches this prototype, it's a perfectly fine function to call back. Of course, when the compiler sees this, he replaces uppercase findFunc with the rest of this stuff here in the type defines. So we don't have to code that mess in here. It makes it convenient for us. Of course, in our code then, if find over here is a pointer to a function, then you might think, duh, what we need to do is dereference it to get to the function. So you might say, well, in order to call this function find in our findNode function, we're going to have to put a parenthesis around dereference find, passing it x and y. That's the hard way to do it. The compiler does it for us. You can't just say dereference find, because this will create an error. This is saying find is a function, go call it, passing an x and y, and it's going to return a pointer, and now that you've got the pointer, dereference it. And that's why it's an oops. We have to have the parentheses around it again. But we don't need it. We don't need this awkward construct. We don't say the quantity dereference square root and pass it z. We don't say the quantity dereference sine and pass it angle. No, we simply say go call square root passing it z and go call sine passing it angle. So all we need to do is say go call find passing it the two values, making it rather simple. All right, let's look at our code for a bit. Here is our link node structure with the forward, back pointer, and the data pointers. There's our complicated find function. And our double linked list class has 4 data members, pointer to the first one in the list, pointer to the last one in the list, and on the current pointer to keep track of where we're at as we're iterating our way through. And for convenience, we'll keep a count of where we're at. We'll have a constructor and a destructor, and we'll have an empty list. Now, one footnote about emptying the list, which I usually stick in the header files, is this. We can delete our nodes very nicely, but the client is going to need to be able to delete his own user data. We don't know what we're storing. We can't delete a void pointer, so I usually put in some kind of sample coding that gives the client, the user of our class, some idea how he has to clean up after himself before, otherwise he'll leak memory. We'll have an added head and an added tail, insert after and insert before the current nodes. In all 4 cases, the client will pass us the data, whatever it might be, a pointer to whatever he wishes us to store in the list, and we'll do it. We'll be able to delete the current node we're on, and here comes our find function so the client can iterate his way through the list looking for a match. And again, notice find will be the client's function that's being passed, that we're calling his function here from within ours. And again, I'll typically give some sample coding in the header file so the client can figure out how to do it and how to code his find function. And then we'll have some simple little helper files to deal with it. Then we need a client program. In this case, I decided we'll pick on phone numbers. We'll make ourselves a little friends phone directory listing. So what we're going to store in the list in these next series of debugging samples will be phone directory structures. First, we'll store a record number so we can keep track. This will be the unique ID, because who wants to try to remember how to spell everybody's last name for a lookup? We'll have 2 character strings, first name, last name, relatively short, 11 and 21 characters, 10 and 20 for example. And then for simplicity, I kept the phone number as character strings as well. The program is rather sophisticated, and we aren't looking at the whole thing today. We'll pick up more of these functions in subsequent debugging lectures, but for today we'll be able to load the phone book. It will need to input 1 set of phone data at a time and load up the list. We'll be able to display the fancy phone book, empty it out. We're going to have a menu of things to choose from, namely being able to add another friend to the listing, delete a friend. We'll be able to look up a phone number, save it, and that sort of thing. I did not provide us an update function. And the main program then creates an instance of our double linked list class called phone book. We'll load the phone book from an existing file. The existing file has just a few friends: Tom, Betsy, Ann, Henry, Lori Ann, Harry, Rusty, and Jennifer. Come back to that list in a moment. After we load it, we'll display it in a very fancy form on the screen, and then we'll go through a menu asking the client what he wants to do. When he finally is done and quits, we'll empty the phone book, and then we need to check for memory leaks. Notice that when you're checking for memory leaks, we have had to call all of the destructors for all the classes and objects in our thing. And notice I put an extra set of brackets around the entire body of the main function. This end bracket here guarantees that all destructors are called, so that when we do check for memory leaks, we'll get real memory leaks. So when we actually run the program, what it's supposed to do is this. It'll give us a nice fancy display of our current phone numbers, and then our menu of what we want to do, and for today we'll simply exit out and be done with it. But that's what it's supposed to look like. A nice, neat listing. Okay, now let's take a look at the debugging situation. Today I've got a very simple bug we're going to find, but I wanted to illustrate a new feature of the debugger you might not be aware of. First, let's start it without debugging and see what happens, and it isn't going to work. Well, looks like we got the first name, and if we look back at our list, we got Tom and Jennifer. That is the first and last entry. All the other friends didn't show up. Well, let's exit and see what happens. Oops, memory leaks. Ugh. So in this case, we know that we've got memory leaks. Not a good sign. So what I'm going to do for today is stick a breakpoint down here at the return 0 and debug until I get to that spot. I'll hit a 6 because we know we've got trouble. And now let's take a look. Down here it says we have memory leaks, and if we look over here, we've got a whole slug of memory leaks. Here's a nice trick. Rather, we could certainly go in here and dive through all that complicated coding, trying to figure out how comes all the records in the middle didn't get in the list, only the first and the last made it. But instead, let's look at memory leaks. What the heck is it? Here's another interesting trick. Under the debug, there's a menu for Windows, and under Windows, there's one for memory. This allows you to look at memory. Let's open a memory window. And I'm going to come over to the output window where we had a block that was leaked. I'm just going to pick on one of these. I'll select it, copy it, come over to the memory window, paste it in there, hit the enter key, and now in this window it is showing us the contents of memory that were leaking. And if you notice, here we are seeing the hexadecimal representation at the address, and over on this right column we're seeing the ASCII characters that they correspond to, if there are any. Well, we know we've got text over here. There's Betsy and there's Smith. So it looks like we're dealing with one of these phone directory structures. Well, if we may remember what the structure looked like, what the phone directory structure looked like, I'll scroll back up to it. We have a record number first. That's an int. That's 4 bytes. And here's the 4-byte integer. Of course, it's stored in backwards order. So we're looking at record number 2. Record number 2 was leaked. Of course, it didn't even show up in the printout. So read the longs backwards, 00002. Here is Betsy. There's the ASCII code for Betsy. Ha, the 42 again. And that's a null terminated string. Even though it was 11 bytes long, that 00 marks the end of the character string, and the rest of the characters are padded with gobbledygook until we get to the end of the field. Here comes the S of Smith, the X53, and it goes to its null terminator. And over on the right column, you can see the Smith portion of it. And after that, here's the area code and the person's phone number showing up. So we can actually see that one of the things we're leaking is the person's, all these phone directory structures, phone listing structures. Notice that there's also another one that's leaking. It's only 12 bytes long. Of course, you might think, well, gee, 12 bytes? What could be 12 bytes? Well, another thing we can do is go to our debug windows, go down to memory, and open a second memory window and paste our address in there. And we're looking at 12 bytes. There's the first 4. There's the second 4. 3, oops, got 5 of them. And then there's the last one. And notice what that looks like. All zeros looks like a null pointer. And our data blocks are around 796220. Again, remember the numbers are backwards. There's 794F85. It looks like this is a forward pointer pointing somewhere, and here's a back pointer. So what are we leaking? We're leaking one of these link node structures. So it looks like we're leaking constantly the data and the node, the link node. There's one, and then here is Ann, and above Ann is the 12-byte block that contains her, and there's Henry, who didn't show up, and there's his 12-byte block that got leaked. And here's Lorianne, didn't show up, and her 12-byte block that got leaked. And there's Henry, and then above Henry is his 12-byte block, and he didn't show up either. And then there's Rusty, and there's his 12-byte block that got leaked, and so on. So it looks like we are leaking memory like mad. Well, since it's not much else I can do, I'll stop debugging at this spot. Now we can proceed to dive into the code. Where should we look? Well, all we've done, if we look at the main program, all that we've done thus far is load the phone book and display it. We haven't done anything else with it. And if we load the phone book, all we're doing is allocating new phone directory structures, filling them up, and adding them at the tail. The key for today is we're adding them at the tail. So all we've done is simply called add at the tail a whole slug of times. So it would make sense we should look at add at the tail. And if we come in and add at the tail with the client's data, we need to allocate a new link node structure. And again, if we don't get it, abort the program. Now that we've got it, add one to the count and store in the pointer news data pointer the client's data that we're supposed to store on this node. Now, if we're adding at the tail, there won't be anybody after us, so the forward pointer would be set to 0. And then if the tail pointer does not exist, we have a completely empty list, then we go down to the else clause and simply put the head pointer and the tail pointer all pointing to this new node. And of course there won't be anybody in front of us, so the back pointer will also be 0. And then we'll set the current pointer to the current one we're on. If there's already items in the list and the tail pointer exists, then we'll come along and set the forward tail pointer, which is pointing to the very last one in the list. Its forward pointer now points to us, because us will be the last one in the list. We're adding at the tail. And then our back pointer, we're going to point back to what used to be at the tail. That'll be tail pointer. And as you can see, I commented out the bug for today. What we then need to do is reset our tail pointer to point to us. We are now the back, not what used to be there. And that's our bug for today. So if we take that out and rerun it, now we have all the items appearing, and when we exit, we have no memory leaks. Yay! We've solved the problem. So the takeaway for today is remember that sometimes checking for and where you have memory leaks, checking where those are occurring, sometimes can lead you and provide valuable clues as to where the actual bug is located. Furthermore, the debugger has, in the debug view, the ability to actually go examine blocks of memory. Of course, the debugger does not know what's there, so he shows it to you in hex format and corresponding ASCII characters, if there are any, that correspond to it. And that can be very useful in debugging in certain circumstances. So remember, if you've got memory leaks, perhaps rather than diving into the complicated code to see where the boo-boos are at, see if you can spot where the memory leaks are at, and they may give you a valuable clue as to where the real error is at. We will next time look at even more complicated problems here in debugging with these pointers using this same double linked list class. Thank you.